Where are you going with this thing?
There we go. At least we have some sound.
We cut that on tape, buddy. Okay. This one's not looking good on the screen. Testing, 1, 2, 3.
Alright. I don't know why I was having... The sound is not going to be great because we're using...
If you have any questions, feel free to drop them in the chat. Mod Spanish guy.
What's it called? Like the laptop mic instead of this mic.
Oh, yeah.
I don't know why. Alright, anyway. We're back. And I think last time we were working through like a rocket lifting off, and I think now we're at like Galileo and looking at like the effect of drag and whether or not like mass changes speed. What do you think, like current like gut feeling? Does heavier mean faster for skiing? What do you think? Yeah.
I was just like intuitively say I don't think it does, because I feel like if it did, you see a lot more like I don't know, big guys skiing. Instead they're like they're like most skiers are like small fit people.
Pretty
but
small.
If it was about speed, you put big guys on the slope, you know?
Okay. Yeah.
I think that intuitively, like heavier, more gravity, you could go faster, but I feel that you're like
so heavier, bigger force of gravity, right?
More surface area for drag.
yeah.
Okay, surface area. So let's see. How does this one look?
You're we should make uranium skiing. They're more dense and faster.
All right, so what do you think we should start with if we're talking about like speed and acceleration and considering forces that cause these things?
Free body diagram?
Free body diagram would probably help, right? That's like, no matter what, you could always start every problem in not every single engineering problem, but most engineering problems, if you start with free body diagram, it's a good way to just identify like what are the causes of things changing. So let's start with that. What forces are there? How are they acting on it? What are the assumptions that we're making that we can like start making some kind of prediction here? So what do you want to? How do you want to start that? At least that's what I think. Start with free body diagram. Do you know what Galileo's claim was? This is something not everybody is like into the nerdy history of kinematics and philosophy and science. What was Galileo's claim? Does anybody know? He's known as the father of kinematics. Yeah, so Galileo was the first one to notice that like acceleration is constant, like the acceleration due to gravity is constant, and whether it was like rolling down an incline or dropping like out of a tower, it didn't matter how big the object was. Speed was always proportional to time, distance proportional to time squared. So that was like Galileo's big claim. So according to Galileo, he would say every skier, no matter what size, weight, shape, they're all going to get to the bottom of the hill at the same time. That's what he thinks. Let's see where we can go from there. Yeah, that's fine.
I'll draw like SpongeBob or Peter Griffin.
Why don't you draw a woman? You should be more gender inclusive.
No, I don't think I will.
They already say the C on plus for Rosa Parks. They did. The UConn bus, I couldn't sit there. Parks is supposed to.
Yeah, they want you to stand up like her. That's the point.
Well, at least they didn't put the post in the back of the bus, because that would have been an unfortunate.
Alright, we got a skier. We got
He was in the middle of the bus, they compromised.
we got the force of drag. We got the force of I guess we call it the weight force. We got weight force. We got parallel to the slope. We have force of kinetic friction, right?
It's fine.
Yeah.
What else? Anything else, boss?
Drag.
I already put drag.
So you go weight, no.
Bro, if we like, why don't we have football players skiing? That's what you know, like they're big guys. Right? I see a bunch of skinny people on the slope.
If you lose control,
Nah, dude, I'm out there.
Yeah? Put me in, coach. Put me in. I don't know how to ski.
I'm like 285.
I might try. Yeah. Absolute boss. Oh my god, we hit 80 subscribers, guys. I'm one of those crowd.
What?
Yeah. We started off like the semester with 62. That's huge growth. That's huge channel growth. Oh, nice freeway diagram here.
No. Is your guy going up?
No, he's like he's going down. He's going down.
yeah, except for the nose.
Oh, the nose. That's actually too.
Or like a hand.
Or like you can see that he's skiing downhill, so it'll go down.
Or maybe you could put like your skiing pole.
So actually, the weight force is the only thing making you go down, right?
Yes.
So is it because bigger people have a different center of gravity?
No.
Are we sure?
Bigger
Bigger
people have
people
more
just go
gravity.
faster. Like,
Why though? That doesn't. You can't say that.
No,
Because they're bigger.
Because they're heavier.
because if you think about it as them falling off a cliff, they're gonna fall faster. So they just
Oh my
fall.
God! There's a whole ass thing about this, bro. When they went to the moon, they dropped a feather and a hammer. They fall at the same rate because there's no air resistance. I don't understand the question. I'm self-aware. Like I know that I'm slow, but
No, heavier.
oh wait, does this have to do with the no? Time out. Does this have to do with the normal force? Because the normal force is based on weight. That's what it is.
Yes. It's angled.
No, so things do fall at the same speed, but there's a normal force here because there's contact. Look, your normal force is no. Shut up. Your normal force is greater if you're big. If you're a big boy, your normal force is accordingly big.
So I did see like MG.
Claim.
Did anybody? So mostly I saw like constant slope. That was sort of the most people's initial assumption. Sounds good. But I think that's a good place to start, right? Like if we can figure out how fast you go for a constant angle, whether you're fast or slower, then we could always introduce like loops and moguls and all that. So that's fine. So we'll say like going down, so normal is normal to whatever slope we had, right? Some kind of like alpha slope. And then I saw like drag and friction. Where are those pointing? Kind of up the slope, right? Unless we're traveling up the slope, but probably we're skiing downhill. So we got like F friction, F drag. Yeah.
What's the symbol for angle that you have?
I used alpha,
Okay.
like a goldfish.
So, do you want to see the alpha, not just theta?
I don't. Yeah, it doesn't matter. No. You could write out the word angle or slope or this is just my own process. Usually theta I usually think of that as like angle of a body, like a moving angle. Alpha, I use that as like some kind of constant, like alpha, beta, gamma. Those are usually constant when I write them. But you can use any system you want as long as you know what's constant and what's kind of changing. Do we need like, is it okay to call it like a point mass assumption? I don't care if the skier's tumbling. Maybe we would care if things would change, but it wouldn't really be the same like skiing, right? So it's okay to say like all the forces are going through center of mass. There is no rotation. Like some of the moments is zero, whether or not we consider them. So that's fine. All right, and now I've heard a few hypotheses. 1, bigger mass, bigger gravity, faster. What do you think? You're bigger, you have a bigger force of gravity, that means you're gonna move faster. Yeah.
I would like to share my thoughts on this as a big man. I think that, so like, I was talking about this with my friend. Your mass, like, because your weight force, due to gravity, it's only a y component, and you're going down the slope.
Okay.
You only care about your x component. So mg on its own doesn't actually make you go faster. The force of friction, the force of drag. Let's assume we have two people of the same size but different mass. I don't know, one's like more dense or something.
Okay. Yeah. Throw some weights in your shoes,
put
right?
Ankle weights on or something.
Yeah.
So the reason you go faster if you're bigger is because your normal force is dependent on the weight force. And if you have a larger weight force, so like you can have a larger weight force but not go faster on its own, but the x component of the normal force vector will be larger if you're heavier.
All right, so in that case, we don't need drag or friction, right? We could just say normal force and weight is the one thing causing faster, slower. So we could explore that. And that's why I was kind of writing up this hypothesis is like, if mass is the only thing, if bigger mass and bigger gravity is the only thing creating faster motion, then we could say drag and friction are basically zero and go from there. Kind of a good start. But did you not want to do that?
I was just going to say,
yeah.
Off of what he said, gravity, even though gravity's acting straight down, you're on a slope, so it is affecting the x momentum.
So it does affect like forward,
yeah.
Right?
And normal would be perpendicular to the slope, so it doesn't affect x at all.
Okay.
It just normal changes your friction force. So.
Do you know this, like similar triangles? Have you done this one before? Okay, yeah. We have like alpha slope, so the alpha, our sine component is the x component of our, all right. So mg sine alpha, and you can use any angle you want. I don't know why I keep making it look so weird. So mg sine alpha, a normal component is not in the downward direction, at least if I'm saying that's like, I'm looking at the unit vector along the slope in this way. You can set it up as like x and y components, and then you solve for max, may, but then you have to figure out that ax and ay have to be related because they're on an angle. Just saves a little bit of time if we just rotate that x coordinate just a little bit, just by alpha, equals ma. And that's all we need, right? At least if... Ooh, something canceled?
So then it doesn't. That's what she's on.
So now we have A equals G sine alpha. And there is no mass, like no matter what. Like if all we're considering is normal force and gravity, yeah, Galileo's right. And a lot of times that is the case, right? That friction and drag are not really affecting. A marble rolling for 1 or 2 seconds is not moving fast enough for drag to affect it, and friction on a marble rolling on a hard surface is 0.001 or 0.0005, something pretty small. All right, so we need something else, right? I did hear, so another thing that I heard was like friction, bigger mass, more friction, which means slower, I think. Or did someone have a different, bigger mass, more friction, faster? That's what I would think. Like, at least when I had heard like a little bit of what people were kind of thinking out loud. Not to like say your thinking is wrong. It's more just try it out. We'll figure it out. What do you think? Bigger mass, more friction. Is that going to be slower? Maybe like a yes? Some yes? Yeah? All right, let's prove it, right? So now we have force of friction. And I'm kind of separating it out for us into that free body diagram of like the slope gravity and normal gravity components. So try it out. What do you end up with for, what does MA equal in this case? Yeah. Mu NG. Nothing else?
Oh, and then add the NG sine alpha.
Mu MG?
Subtract it.
Is it mu MG? Like that?
Or with the cosine.
Oh, and a cosine? I can't draw alpha today. Same direction?
Opposite direction.
Okay, negative. And then plus mg sine alpha. Bigger mass, less acceleration. Cancel, still cancels, right? What are we doing wrong? Or right? We're doing things right. Because it's easier to start simple and keep adding a little bit until you end up where you want to be. Because it's a lot easier to do this equation when we already had our first equation. It's scrolling up in a second. I think it's easier to just like tack on a little bit at a time. So we still have acceleration, doesn't matter. So friction is friction. It changes your acceleration, but it's not bigger mass. Although there's bigger friction, it's still proportional to mass. Yeah.
I think that maybe if you have more mass, you have more momentum, so you're less resistant to the changes due to friction and drag.
So that's what we're saying here. Like, that's what this equation is saying. Is like MA is our change in momentum, right? Because we could have said, like ddt of mv is all of that, but bigger mass more momentum, so we need bigger forces to create that. But if we have bigger forces, then we have more momentum. Yeah. So it's kind of an exercise of thinking about, like, if it's if the force is dependent on mass, then it ends up being like acceleration is independent of mass. So what do we need now? Something else? Maybe drag, yeah. Because that was the last force that we had in our first like big free body diagram of everything. So the last thing is that FD, what do you think? Force of drag is bigger on more mass? Like more mass, less drag? More mass, same drag?
Wouldn't it be more if it was bigger surface area of the mass? Like if you have
Okay.
a really small mass, it's the same weight as something that's really big.
Okay.
Depending on the material.
So maybe surface area dependent? What about, is mass surface area dependent? No? What's mass?
So volume times density.
So like volume, so your surface to area, right? So maybe if you increase area by 2, like your volume doesn't necessarily increase by 2. A lot of times it increases by like 1/2 or something. So bigger mass is bigger volume, but not, and maybe bigger area, but not the same scale.
Assuming density of a person doesn't change.
Yeah, I think for the most part, a person is just like about the density of water, slightly lower, right? Because most people float in water. So I think for the most part, we're all like dense, neutral buoyancy in water, maybe a little bit lower than that, like 1 gram per centimeter cubed. Is that right? Or no, millimeter cubed. Millimeter cubed? Centimeter. Now I can't remember. Anyway, 1 milliliter is 1 gram. I know that for like measuring out coffee. So what is MA in this case when we consider all the forces that could be acting on our skier? Yeah.
mg sine alpha minus un minus coefficient of drag times area times density of the fluid.
Yeah,
velocity squared over.
FD. Yeah. Okay. Nice.
Won't the equation be the same as it was last time? Except now we're just subtracting force of drag.
Yeah, but it's not related to mass, so you can't cancel it out.
Right, so force of drag therefore must be different on bigger and smaller masses. of assuming same surface area, right? I guess if you're big, I guess if you're the same size, right? I guess if you have the same surface area, but you have more mass, air resistance becomes more negligible, right?
I don't remember.
No, because you know how like there's those really tiny bugs that like a fairy fly basically its wings. It's not really wings. It like scoops itself through air because it's so small. So the smaller you are, the more dense air is relatively. So the bigger you are, at the same, or like the more mass you have at the same size, the less relevant air resistance is because you're able to push through.
I think he's making
I still think air resistance is important. I just think like,
Dude, I'm calling.
That shit is so negligible. What?
Dude, I'm calling. Damn, you gotta cut this on this part. I do not want this.
No, me neither. Huh? Friday at the end of the day, but it's like a soft day because nothing's actually
Yeah. And then the quiz is like Monday, Tuesday next week.
And he said, I mean, the thing is though, the problem after this is revision, which is something. I think it requires seeing textbook, which is really unfortunate.
isn't textbook physics fun?
Exactly.
Oh no, he posted like excerpts of it.
Yeah. What, the program?
Yes.
Yeah, I think we're going.
I know.
That seems to be the course of study. So it's the same as it was last time. Except you had, or you said,
by the time it took me to do my thermal homeworks, I kept having to make up for it.
Yeah.
Gotta get started on the next thermal homework.
Oh my gosh.
no, go review session because the TA told me he's gonna starting this Thursday. We're doing homeworks during review
Yeah,
session.
I actually emailed them to ask to do that. I asked them to record it too, which they did the first time around, but it said him drawing on there.
He was pretty. No, it's the other guy. And so that was a different guy. Anatol, he's a star, dude. I went to his office hours. He's an absolute boss. He's running it Thursday. Definitely tell your friends to go because he's just doing the homework.
Well, I mean, they recorded. I'm a commuter. I drive an hour, so and then I have the last class on Thursday. I have thermo, so I have to wait around for 6-7 hours.
That's based. Don't wait. Yeah, don't wait for that. Well, just tell your friends to watch the recording.
It's very unfortunate.
They weren't gonna record it until I emailed them about it, and then they're like, "All right, we'll try to do it." And then whatever happened in the last class, try to draw on the computer, which one?
He was having a hard time drawing that computer.
I was
think
talking to Anatol, but I'm not sure if Anatol has like an iPad or something like that.
he does because at his office hours he had like the Surface Pro, and he's gonna be fine.
Even the verbal explanation helps.
Yeah. Well, the thing was the practice problem we did was actually kind of stupid.
The first one?
Yeah, with the solar panel.
So stupid.
That was like lobotomizing to watch. It was like.
I was like, what are we doing here? Why are we doing this? It's nothing like our homework. It's nothing like what we learned at all.
The thing is, though, thermo's still my favorite class. I just think the content is really interesting.
Yeah, it is. It's just
they don't make it easy. Yeah. I guess they should. If anybody could be an engineer, that would look at me concerning.
Well, I mean, I missed the first like 15 minutes of class yesterday. I was late. Didn't he say something about tests being like less question or less like dense questions?
Yeah. And he said that since there's multiple questions, they won't build on each other like the homework. So say for like question 1, if you get like the wrong enthalpy, question 2 is a completely separate system. So it's not like your error will carry through, which was good. But one thing he did say was concerning is he might do it on lockdown browser multiple choice. So there's no partial credit. I'm like, nah, bro, paper copy. Let's see it. Give me that partial credit, man.
I need it until like help me.
Give me that partial credit. I don't know, man. I just work here. What is the force of drag?
That kind of stuff.
Oh, wait.
It's in the top like question. It's like F equals 1/2 CD A P squared.
We probably should have started by writing that because it doesn't have an F. Yeah. Such is life.
Yeah, it says it right. You probably could have assumed that. I didn't read all the way through.
I'm low-key slow as hell. I'm not surprised I missed that.
How are you doing so well in class?
Bro, I'd be guessing, checking my way through college. It's worked this way. Okay.
I'm just gonna write like, yeah. All right, we'll write it out.
Yeah, my question is, why do they make the thermal homework so hard? Like,
He said the first.
I think the first one,
second
he might have been trying to
was
weed out the unworthy thermo students.
All right.
Those who are unworthy to discuss the engine.
How does this look for our equation? You concur? Looking good?
Can we discuss the variables involved in the last term?
Yeah, I think that would help, because then we might actually be able to say something worthwhile about it.
Yes.
Yeah.
So for the force of drag, why wouldn't you include like the cosine, like cos alpha, if you're on like an incline?
Oh, why isn't it like just a component of? So drag is always going to oppose wherever you're going. So whatever your velocity is, drag is opposite. It's in that direction but opposite. So in this case, because we said like roughly like our x-axis is the motion axis, drag is parallel to it. So that's why we can just like not worry about the components of it. Yeah, that's a good question. And most of the time we would have like, even if you're considering like an airplane that's moving, really it moves in like 3 dimensions, but you might have like a drag off the nose of the plane and then maybe a drag like perpendicular to it if it's like falling and moving forward. So usually you'd have like 2 separate components. Also because there's 2 different areas depending on how you're looking at the object. All right, so let's break down force of drag. Rho is density of air. I always forget. I think that's like 1 kilogram per meter cubed, like 1.00 something. CD is drag coefficient. Could be for like general objects, it could be anywhere from like 0.1 up to like, I think a parachute is maybe 3 or something, 3 or 4. Like if you're trying to increase drag, I think you can get up to like 3 or 4.
So it's just surface area dependent?
Material.
No,
material
it's geometry. So drag coefficient is purely geometry dependent. Like if so 2 spheres have the same drag coefficient, just full stop. It changes a little bit, like a golf ball versus a ping pong ball. Those have different drag coefficients because golf ball has dimples. So now it's changing, it's creating like little vortices inside those dimples. For us, when we're just considering like the dynamics of an object, drag coefficient is a table lookup sort of thing. Like once you have it, that's it. You can assume that there's some error in it if you want, but it's just there is a value of drag coefficient. So yeah, could like rough estimates, like 0.1 to 3. And then we have A is cross-sectional. And that one's kind of weird because it's not like surface area of the object. It's actual like cross-section. Like what is the air actually have to move around? And then V is the speed. Like not velocity, it's like straight up how fast are you moving through. I guess really it's relative speed. So if you do have a tailwind, then there's slightly less drag, but so we'll say relative to fluid. Rho, CD, A, V. All right, we got them all. So what's different about force of drag versus friction and weight? Not mass dependent, right? So if one assumption that we could make to say force of drag is going to change, like the speed as we move down, is we could say we're both moving through the same air. Probably a good assumption. we both have the same drag coefficient, like we're both roughly the same shape. And then speed we're trying to figure out, but maybe cross-sectional area is close enough, like it's the same. One thing we could do is say that it is the same, and then we would have A equals G sine alpha minus mu G cosine alpha minus 1/2 rho CD A. Yeah.
So does like drag depend on both like the object and the medium that it's going through, like for the coefficient for the speed?
Does it depend? What do you mean, like by the object, like the material?
Yeah, like the material going through like a fluid or whatever.
So I think the general kind of theory of aerodynamics and like fluid mechanics would be, it's not that the material matters, but the shape of the material. But you can get like pretty deep into the weeds into aerodynamics, because like if you have like nanostructured materials or like the Olympic swimmer shark skin suits, they have like micro fin designs to try to reduce drag, like reduce that coefficient on their suit, and all of that is like high-tech science to try to reduce. And really, like what it ends up being is like CD times A is like your kind of drag area. So the smaller you can make that CD, it's as if you're a smaller object moving through the fluid. You have a smaller cross-sectional area. Yeah.
Might be a stupid question, but is there any reason you moved the speed off to the side, or you just tight with it?
I moved it because I was trying to say like solve for, like thinking about like if I was going to solve for speed, okay, where would I put it? That was my thought. Okay. Yeah. Yeah, do you know how we could figure out how fast this person's moving? Like what's the equation? How would we solve for that? Like max speed for the skier.
Integral.
Take an integral? Do we need an integral?
I think if we set acceleration as 0.
If A is 0? What do you think? We need to integrate over time, set something equal to 0. If we're at max speed, are we going to keep speeding up? No. It's called like the terminal velocity. So like when A equals 0, now we could say, so we could say like V terminal A equals 0, which is that G sine alpha minus mu G cosine alpha. But that's why, at least I was just thinking about like that next step. If I wanted to compare like how fast, what's the max speed these two people are going to be moving, that was my thought. Was like get all that stuff over on the left-hand side and then solve for v squared that way. Yeah.
Why are we able to assume that normal force is mg cosine theta? Are we assuming that it's static, or at least the y forces are static?
That one, oh, are we? Are they not?
Well, I was just wondering, I didn't know if they were.
So n minus mg cosine alpha equals may, at least like if we call this x. So are we making an assumption? Like I mean, I guess like in general, like we're building a model, we do need assumptions, but is this a good assumption to say that MAY is 0? Why is that?
Because you're on the
Not
ground.
sure. Because you're on a ground? Yeah.
You're not,
Not sure, and then on the
as
ground.
long as you're not getting height.
Yeah, so if we're on, the one thing that we're doing here, like, and we didn't really like discuss it, but if we're saying like motion is happening along that slope, we're creating a constraint. Like there's a constraint on the motion, and so normal force and mg cosine alpha have to be equal in order to maintain that constraint that we're moving on a slope. It's not that that's always the case. Like if you hit a bump, you can have, like now you're moving up, but implicitly we said these forces have to be equal because we're only moving along one direction. So because motion is x-axis, then it's all there. All right, still have like 5 minutes. Oh yeah, that was 2m. All right, so what do you want to do here? We've got an equation. What can we do with this? You want to plug in values, find relative changes. Where do you want to go?
You could like plot it with a software,
Or we could plot it.
Can't you solve for V? Or no?
We can solve for v. Yeah.
So if you solve for V, won't that give you the speed based on mass?
Yep. Yeah, you want to solve for v in terms of mass? Is that the plan?
Because then it'll show you that since mass is in the denominator for air resistance, it's going to be like the higher mass, the less the air resistance
Higher mass,
or drag.
less drag. Yeah, less effective. Like drag was the same force, but mass went down, so force has bigger effect. Something like that. Yeah. How's that sound? Yeah, other ways, like you can go and look up what is CD for a skier, what is the area for a skier. Yeah.
So if you're like not on a slope,
Yeah.
would the only like force applying to you be the drag and like gravity, and then that's how you could solve for say terminal velocity?
If you're not on a slope?
Yeah, because if you're on a slope, you have that g sine alpha term and the new g cosine alpha term. But if
Yeah.
you're like directly straight, sort of angle is 90, and those two terms cancel out.
Yeah.
Over, that's how we're gonna put it.
Yeah.
Then like the only forces that would be applying to you is like your weight and the drag.
So like Looney Tunes, sort of?
Yeah, I guess.
Yeah, we can do that. That would save us some efforts. Hopefully this is all theoretical. We're not going to send anybody down a cliff. I think even, what do you think like the biggest slope, like what's like the biggest slope you've ever been on? Do you know what the angle was?
Probably not super small.
Rock, yeah, so rock climbing is like pretty sharp angles, but
The thing about that drawing is, isn't that just free fall and then mass doesn't matter? I guess it does because the thing we talked about.
yeah, now mass definitely matters, right? Because we have ma equals mg minus ft. So now we've got ft over m, just a straight up. 45 degrees, you think?
When I started, I was probably like 55 degrees.
55?
Just for the start, not the whole time.
55.
You couldn't see over the edge.
Yeah, okay. I hiked up the backside of Half Dome, and at the steepest point, I felt like I was rock climbing, like you were holding on to belaying things, and I would have thought, like, if I had not known anything about the angle, I would have assumed I was climbing up like an 80-degree angle. But after, when I looked it up, it said the biggest slope, like at the max slope as you come up the backside of this like mountain, is 45 degrees. And I'm like, what? And even at 45 degrees, I'm like holding on to ropes, trying to keep my footing steady. So my guess is 45 degrees is pretty steep. I mean, I've been in like mini ramps for skateboarding, and those, unless there's an actual vert, and usually the vert's pretty short, at least for like amateurs like me. I don't know if anybody's like professional skateboarders, but the vert section, like the actual 90-degree slope, it's like inches, you know, and then it quickly transitions into 45 and back into like so probably the biggest slope you've ever seen is maybe 30 degrees, my guess. I don't know. At least like Black Diamond sort of stuff. I don't think it hits 45 degrees. At least maybe it does for like a little section, and then back to like something that still feels kind of scary. That's my guess. I could be wrong. I would love to know, like, what are the max slopes on every mountain, then I can avoid them. All right, anyway, we spent the whole time talking about drag and forces. Hopefully you have your own idea of like whether or not this proves or disproves mass does affect speed, and then you can process your way. Thanks a lot.